Hope you all are doing good. I am Anjana from Learnohub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 12 Radioactivity. We will be discussing the topic nuclear fission and fusion. Also, we will be solving questions from exercise 12B. Are you ready for the session? Let's begin. First, let us understand what is nuclear energy. We know what is nuclear change. During a nuclear change, there will be a change in the number of nucleons. Okay, we know inside an atom. If this is an atom considered, we know all the nucleons are concentrated inside the nucleus. It contains protons and neutrons, and also the electrons will be revolving in circular orbits around the nucleus. So during a nuclear change, what happens? Either the number of neutrons can change or the number of protons can change, or both the number of neutrons and protons can change. Okay, we have said about alpha decay, beta decay and gamma decay. During alpha and beta decay, what is happening? There is some change happening. Alpha decay, during alpha decay, there is a decrease in the atomic number and mass number. When mass number decreases, it means that there is change in the number of neutrons. When atomic number changes or decreases, there is a decrease in the number of protons, because atomic number is determined by the number of protons. Okay, what happens during a beta emission? During a beta emission, a neutron is changing into a proton. Okay, and during a gamma emission, there is no change in the nucleus. Only an excited atom comes to a stable atom, okay, to its ground state by emitting gamma radiation or gamma ray photon. Okay, so this we understood what a nuclear change is. Now during a nuclear change, what happens also we have understood. So it is not necessary that always. So when a nuclear change happens, what happens is there is a decrease in mass. Now where does this mass go? Okay, we will be having a reactant part and a product part. Okay, in the product part and reactant part, when you take the masses and sum it up, you will understand that the mass of the reactants, the total mass of the reactants will always be greater than the total mass of the product. Okay, which means some mass is escaping out. So where does this mass go? This mass will get converted into energy, and this energy is called nuclear energy, and this is according to Einstein's relativity. According to Einstein's relativity, you will study this equation, that is E is equal to mc square. Okay, E is equal to mc square or delta mc square. What is delta? Delta is a small change. Okay, delta m is change in mass. Okay, this will be taken in kilograms. Now what about C? C is the speed of light, whose value is 3 into 10 raised to 8 meter per second. Okay, and the energy will be expressed in joules. Okay, so according to Einstein's relativity, E is equal to mc square. This mass which escapes out gets converted into energy, and it is released as energy. Okay, so understood what nuclear energy is? Nuclear energy is released during a nuclear change. Energy equivalent to mass 1 kilograms. So we said that mass and energy are interconvertible. Okay, so when 1 kilogram mass is lost, the amount of energy released is what we are going to find. We have energy is equal to mc square. Okay, E is equal to mc square according to Einstein's relativity. Now, what is mass? Mass is given to be equal to 1 kilogram. C is equal to 3 into 10 raised to 8 meter per second. Both these values we know. So putting in the equation, we get E is equal to 1 kilogram into 3 into 10 raised to 8 whole square meter per second square, which is equal to 3 square is 9 into 10 raised to 8 whole square is 10 raised to 16 kilogram meter square per second square. The unit of energy is joules. Okay, so energy is equal to 9 into 10 raised to 16 joules. Okay, now we got the energy. So there is another unit of energy which is kilowatt hour. 1 kilowatt hour is equal to 1000 watts into 3600 seconds. Why? Because we know that 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. If 1 minute is 60 seconds, then what is 60 minutes? 60 minutes will be equal to 60 into 60 seconds, which is 3600 seconds. So 1 hour is equal to 60 minutes and that is equal to 3600 seconds. Okay. So 3600 seconds. Then what do we get? 3600, again 3 more zeros, watt second. This watt second is joules. Okay, so you are getting 3.6 into 10 raised to 1, 2, 3, 4, 5, 6. 10 raised to 6 watt seconds or joules. So this is 1 kilowatt hour. Okay, 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules. Now, here we have energy is equal to 9 into 10 raised to 16 joules. Okay. We got 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules. Then what is 1 joule? 1 joule will be equal to 1 by 3.6 into 10 raised to 6 kilowatt hour. This is 1 joule. Okay. If 1 joule is so much, then what is 9 into 10 raised to 16 joules? It will be equal to 9 into 10 raised to 16 divided by 3.6 into 10 raised to 6 kilowatt hour. That is equal to, okay, here you will be getting 9 into 10 raised to 16 divided by, this can be made 36 into 10 raised to 5 kilowatt hour, which is equal to 9 by 36 when cancelling. 9 into 4 is 36. What is 1 by 4? 1 by 4 is equal to 0.25 into 10 raised to 16 minus 5 kilowatt hour. That is equal to 0.25 into 10 raised to 11 kilowatt hours. Or you can say 2.5 into 10 raised to 10 kilowatt hour. Okay, this is the energy. So, energy equivalence of 1 kilogram mass is equal to 9 into 10 raised to 16 joules, or 1 kilogram is equivalent to in energy 9 into 10 raised to 16 joules, that is also equal to 2.5 into 10 raised to 10 kilowatt hours. Okay, so this is the energy mass relation. Energy, 1 kilogram energy, 1 kilogram mass in energy. Okay. Next, energy equivalent to mass 1 a.m.u. So, when mass is 1 kilogram mass is lost, we have calculated how much energy will be released. Okay, equivalent energy released. If 1 a.m.u of mass is lost, then what is the energy is what we are going to calculate. Now, what is a.m.u? a.m.u is atomic mass unit. So, mass of atomic particles. Atomic particles is expressed in atomic mass units, or it is also called unified mass. And what is a.m.u? 1 a.m.u is equal to 1 by 12 the mass of carbon 12. 1 by 12 the mass of an atom of carbon 12. Okay. So, 1 a.m.u is equal to 1 by 12 into mass of an atom of carbon 12, okay, which is equal to 1 a.m.u is equal to 1 by 12 into mass of carbon 12 is 12 kilogram, okay. So, a carbon 12 atom contains the number of, that is, if you take 12 kilograms of carbon 12, you will be having inside that 6.02 into 10 raised to 26 per kilogram mole. Okay, in 12 kilogram, there will be 6.02 into 10 raised to 26. Okay, this many atoms. So, for one atom's mass to get, you have to divide 12 kilogram divided by 6.02 into 10 raised to 26. So, then 1 a.m.u on calculating, you will be getting 1 a.m.u is equivalent to 1.66 into 10 raised to minus 27 kilogram. When you calculate this, you will be getting this answer. This is what 1 a.m.u is. Okay, 1 a.m.u and kilogram relation. Okay, now we can find the energy. Energy is equal to mc square. Here mass in a.m.u is 1 a.m.u. In kilogram, we have determined, which is 1.66 into 10 raised to minus 27 into C square. What is C? 3 into 10 raised to 8 meter per second whole square. Okay, so when you calculate this, you will be getting 1.49 into 10 raised to minus 10 joules. So we have obtained the energy in joules. Okay, now we have 1 mega electron volt, MeV. 1 MeV is equal to 1.6 into 10 raised to minus 13 joules. Okay, 1 MeV is 1.6 into 10 raised to minus 13 joules. Then what is 1 joule in MeV? 1 joule will be equal to 1 by 1.6 into 10 raised to minus 13 MeV. Okay. Now, if 1 joule is this much, what is 1.49 into 10 raised to minus 10 joules? It will be equal to, so energy is equal to 1.49 into 10 raised to minus 10 joules. This is equal to 1.49 into 10 raised to minus 10 divided by 1.6 into 10 raised to minus 13 MeV. So when you calculate this, you will be getting energy is equal to 931 MeV. So if the mass lost is 1 a.m.u, it is equivalent to 1.49 into 10 raised to minus 10 joules. It is also equivalent to, that is in MeV, 931 MeV. So this will be the energy that is released. If mass lost is 1 a.m.u, then energy released will be 931 MeV, mega electron volt. Okay. Nuclear fission. Fission means splitting. Just understand, fission means splitting. Okay. So here what happens is a heavy nucleus splits into two lighter nucleus. This is what nuclear fission is. Nuclear fission is a process in which a heavy nucleus splits into two lighter nuclei of nearly the same size when bombarded with slow neutrons. So we know that in a change, okay, in a nuclear fission reaction also, here what happens is the sum of the masses, okay, that is a heavy nuclei and a neutron. Here what happens is a neutron strikes a heavy nuclei and then it splits into lighter nucleus. So when you take the mass of the reactant and mass of the product, you will understand that the mass of the reactant will always be greater than the mass of product, which means there is a loss of mass. This mass lost will be converted into energy. That is, there is some energy released. Okay, according to Einstein's relativity, E is equal to mc square. Now, this experiment was performed, that is, a neutron was made to strike uranium-235 isotope. Then what happens is when this neutron strikes uranium-235, it absorbs, uranium-235 absorbs this neutron, okay, and then gets converted into an unstable nucleus, which is uranium-236. So here you can see that when a neutron is added, what happens? Does the atomic number change? Here the atomic number of uranium-235 is Z is equal to 92 and mass number is 235. We know that the neutron will only affect the mass number. Okay, we know mass number is the sum of number of protons and the number of neutrons. So here the mass number should change from 235, it becomes 236. So here the atomic number is the same, 92, and mass number becomes 236. Okay, this is unstable. So this unstable nuclei, now what happens is it splits into two lighter nucleus. One is krypton and the other is barium. So here for krypton the atomic number is 36 and the mass number is 92. For barium the atomic number is 56 and the mass number is 141. Okay, with this energy is released and 3 neutrons are also released. Okay, now you have to remember one thing, during a nuclear fission reaction, the atomic number and mass number, when you take the atomic number, sum of atomic numbers of the reactant side and product side, they will be conserved, they will be equal. Let's say, so here you can see what is the atomic number, reactant side. Reactant side, atomic number Z is equal to 92 plus 0. Okay, 92 plus 0, that is 92. What about mass number A? Mass number is equal to 235 plus 1. 235 plus 1, that is equal to 236. Okay, so this is reactant side. Now take the product side. Product side. So here we have an intermediate stage. So here again this unstable nucleus also, when you take, you will be seeing that atomic number is same 92, mass number is 236. The sum is 236 here. Okay. Now take the product side. What is the atomic number? Atomic number, we have to take the sum of all these, that is 36 plus 56 plus 3 into 0, that is 0, which is equal to, you will be getting 92. 36 plus 56, you will be getting 92. Atomic number is 92. Now what about the mass number A? Mass number A is equal to adding 92 plus 141 plus 3 into, here you can see 1, okay, of the neutron. 3 into 1, that is equal to 92 plus 141 plus 3, on adding you will again be getting 236. So you can see that the mass number and atomic number is conserved. Okay, so here what happens, the lost mass is getting converted into energy, and this energy is approximately equal to 190 mega electron volt. So during a nuclear fission reaction, 190 mega electron volts of energy will be released. Okay, so this is a basic idea about the nuclear fission reaction. So here what happens, a neutron strikes a uranium-235, it splits into krypton and barium with the release of 3 neutrons and energy. Okay, now this nuclei is formed. It is not necessary that they should be stable. So they come to the stable state by the beta and gamma emissions. Okay, so we understood that when a neutron strikes uranium-235, you will be getting barium and krypton as the daughter nuclei. So here we got one combination, that is barium and krypton. It is not just that combination. So we got that barium-141 and krypton-92 is formed. It is also possible that when uranium, the unstable uranium-236 splits, it can form barium-144 and krypton-89. Also another product is lanthanum-148 and bromine-85. All these combinations can be formed. That is, these pairs of daughter nuclei can be formed with the release of 3 neutrons and energy. Okay, so the first reaction, that is uranium-92-235 with neutron gives the unstable nuclei, that is uranium-236. Here the atomic number 92, mass number 236. It is forming barium-56-144 and krypton-36-89. Okay, now just check the sum of the atomic numbers. Here it is 92, here it is 92, 56 plus 36 is 92. Okay, now 235, here 1. So 235 plus 1, 236, 236, 144 plus 89. That is again 144 plus 89 plus 3 into 1. When you add, you will be again getting 236. Okay, so you can say that the atomic number and mass number are conserved. Energy is released. Now the second reaction, this we have already discussed. Okay, next uranium-92-235 plus neutron gives uranium-236. Okay, it splits into 2 daughter nuclei, which is lanthanum and bromine. Okay, lanthanum. Atomic number Z is equal to 57 and mass number A is equal to 148. Okay, for bromine, atomic number Z is equal to 35 and mass number A is equal to 85. Okay, so 57 plus 35 is 92. Here we have 92. Next, 148 plus 85 plus 3 into 1. That is 148 plus 85 plus 3. You will again be getting 236. So these are the other possible products. Okay. Calculation of energy released in one fission. If we know the mass of the neutron, uranium-235, barium-144 and krypton-89, you can find the amount of energy that is released. Okay, so here we have to calculate. We know E is equal to delta M C square. First we'll find what is delta M. Delta M will be the sum of mass of reactant minus sum of mass of products. Okay, so here sum of mass of reactants. We have a neutron and uranium-235. What is the mass of neutron? Mass of neutron is equal to 1.01 a.m.u plus. What is the mass of uranium-235? It is equal to 234.99 a.m.u minus sum of mass of products. So here what are the products? First you have to take the mass of barium. Mass of barium 144 is equal to 143.87 a.m.u plus mass of krypton is 88.90 a.m.u plus 3 into mass of neutron, that is equal to 1.01 a.m.u. Okay, which is equal to, when you add 1.01 plus 234.99, that is equal to 236.00 minus, when you add this part, that is 143.87 plus 88.90 plus 3.03, you will be getting that to be equal to 235.80 a.m.u. Okay, so on subtracting this, you will be getting 0.20 a.m.u. So we have got the mass in a.m.u, that is 0.20. Now we have to find the energy released. How to find energy released? We have determined the energy a.m.u relation. Okay, so here if this is A, we have 1 a.m.u is equal to 931 MeV. Okay, then what is 0.20 a.m.u? To find the energy, we need to find what is 0.20 a.m.u will be equal to 0.20 into 931 MeV, that is 190 MeV. So this much of energy will be released. So this energy can be in the form of, that is major part of this energy will be the kinetic energy of the barium, kinetic energy of krypton, that is the fragments. Then there will be gamma rays released, okay, gamma particles to bring it to the stable state. They may be unstable, so unstable nuclei can be brought to the stable state by releasing gamma. So gamma radiation, then energy of the neutrons, there is heat, light, etc. produced. So the energy lost will be in all these forms. Kinetic energy, it can be light energy, heat energy, energy of neutrons. Okay, so this is the energy 190 MeV. Controlled and uncontrolled chain reaction. So what is a chain reaction? This is a continuous reaction. We know that when one neutron strikes uranium-235, we are getting two fragments, that is two other nucleus, barium and krypton, plus 3 neutrons. Now here we have obtained 3 neutrons. These neutrons can strike the other uranium-235s. Okay, 3 other uranium-235s are striken by these 3 neutrons. Then what happens? Energy released is going to increase. Okay, so here neutron is striking uranium-235, it splits. Okay, nucleus is splitting, energy will be released, the neutrons will be released. Now these neutrons release. So here you have got the 2 products, krypton and barium. Now these neutrons can go strike other uranium-235 nuclei. Then what happens? Again energy will be released. Okay, for this 3 neutrons will be released. For this 3 neutrons will be released. For this 3 neutrons will be released. So total there are 9 neutrons. Now this 9 neutrons, what they does? They go and strike other uranium-235 nuclei. Again what happens? For each, okay, for each 9 of these, 3 each, you will be getting the products. Okay, again 3 neutrons for each uranium-235 you will be obtaining with these products as well. Then what happens? You will be able to see that this is a continuous reaction. This is a continuous chain reaction is happening, which means energy released is increasing. Okay, energy released It's just not increasing, it is tremendously increasing. Due to this increase in the energy, what happens? It can cause an explosion. Uranium explosion it can cause. Okay, this is very harmful and this is used in case of a nuclear bomb. Okay, so this is an example of uncontrolled chain reaction. So, in an uncontrolled chain reaction, the neutrons which are released will go strike other uranium atoms and release again neutrons. The new neutrons will again go strike uranium-235. Again new neutrons and energy will be released. It is very harmful and it can be used in case of a nuclear bomb. Nuclear bomb explosion is happening in this way. So, understood what is an uncontrollable chain reaction? Next, controlled chain reaction. So, as the name suggests, there is some control. Okay, we are going to control the reaction. Take the same reaction. Uranium-235 is striken by a neutron. It produces barium-krypton, 3 neutrons and energy. Now, we have understood that these 3 neutrons are causing the chain reaction. Okay, we cannot control because 3 neutrons are being released by each uranium. Each neutron, when it strikes a uranium, we can see that more energy and neutrons are being continuously released. Now, what if I made something to absorb these neutrons so that it doesn't cause the continuous reaction? Okay, uncontrolled reaction can be prevented. So, here cadmium rods are used. Okay, using cadmium rods, some neutrons will be absorbed. Okay, the other neutrons will cause the chain reaction. So, cadmium rods are used for this purpose to control the chain reaction. Okay, now the reaction's speed can be slowed down. Okay, the reaction can be slowed down using moderators. As moderators, here we will be using heavy water or graphite. Okay, using these moderators, the reaction speed, that is reactions can be slowed down. So, by this what we understand, the energy released can be controlled and these energy released can be used for constructive purposes. Okay. So, this is an example. An example for controlled chain reaction. Controlled chain reaction is a principle that is used in nuclear reactors. In nuclear reactors, energy released is used for constructive purposes. Okay. So, nuclear reactors. So, these nuclear reactors will be having moderators to absorb. Cadmium rods will be there. Okay. So, for constructive purposes, this is helpful. So, we have understood that uncontrolled chain reaction is the principle behind the nuclear bomb and controlled chain reaction is used in nuclear reactors. Uses of fission. So, we have studied uncontrolled and controlled chain reaction. In case of a nuclear bomb or atom bomb, what is used? Uncontrolled chain reaction is used. So, that is for destructive use. Okay, this is a destructive use of a nuclear fission. So, destructive use, the fission process is used in nuclear bomb or atom bomb when the energy release is fast and uncontrollable. Next is constructive use. For constructive purposes, where it is used in case of nuclear reactors. The fission process is used in nuclear reactors where the rate of release of energy is slow and controlled. So, here this energy can be used to produce electric power. Okay. So, there are destructive use and constructive use for nuclear fission. Okay. Here there is a tremendous amount of energy released in this process. So, in the previous section, we have discussed in detail about radioactive decay. We have said what are the different types of radioactive decay, alpha emission, beta emission and gamma emission. We have also discussed where this radioactive decay happens and all. Today's class, we have understood what is nuclear fission reaction. Now, what is the difference? Are nuclear fission and radioactive decay the same? No, right? So, what are the difference between radioactive decay and nuclear fission? We will be discussing 3 important points. First is radioactive decay. It is a spontaneous process. Okay, we know that in case of a nuclear fission reaction, we need a neutron. It is initiated by a neutron. So, in case of radioactive decay, we don't require any external agent to initiate it. It is a spontaneous process. Okay. Nuclear fission. What about nuclear fission? It does not occur by itself. If the uranium-235 is held as it is, there is no reaction to take place. But it is initiated using a neutron. A neutron is made to strike a uranium-235, only then the reaction starts. Okay, so it is initiated when neutrons are bombarded on a heavy nucleus. For example, uranium-235. Now the second point, the nucleus emits either the alpha or beta particles with the emission of energy in the form of gamma rays, which is not very large. Okay, this is a case of a radioactive decay. We have understood the radioactive decay, emission of alpha. What happens there? There is a change, that is a decrease in the atomic and mass number. Okay, then if it is in the unstable state, it will come to the stable state by emitting gamma radiation. So this was about the radioactive decay. Now what about the nuclear fission? On bombardment of a heavy nucleus with neutron, a tremendous amount of energy is released. So during this, the energy released is lower compared to the energy that is released in the case of nuclear fission reaction. And the nucleus here splits into two. Here, is there a splitting happening? No, right? So here there is a splitting happening. Nucleus splits into two to form nearly equal fragments. That is, the products formed will almost be having the same mass. Next, the third point is the rate of radioactive decay cannot be controlled. So we have discussed in nuclear fission controlled and uncontrolled chain reaction. So if you want, you can control the chain reaction. You can control the nuclear fission reaction. The rate of nuclear fission can be controlled. The energy release can be controlled and it can be slowed down. Clear? So these are the important differences between radioactive decay and nuclear fission. Next is nuclear fusion. We have said nuclear fission means splitting. A heavy nucleus splits into two lighter nucleus. Just the opposite is nuclear fusion. So in a nuclear fusion reaction, two lighter nuclei combine to form a heavier nucleus with the release of energy. So why is energy released? Because there is a loss of mass. When you take the mass of reactants and mass of products, you will see that the mass of reactants, here also the mass of the reactants will be greater than the mass of products. Okay, mass of reactants greater than mass of products, which means there is a loss of mass. Okay, this loss of mass is in the form of released in the form of energy. Okay, this is a nuclear fusion reaction. So nuclear fusion is a process in which two light nuclei combine to form a heavy nucleus. In this process also, huge amount of energy is released as in the case of a nuclear fission reaction. So two lighter nucleus, here deuterium and tritium nucleus combine to form. Okay, it undergoes fusion, release in helium atom, energy and a neutron. Okay, so these are the lighter nuclei, they are forming a heavier nuclei. So for hydrogen, there are three isotopes. One is hydrogen 1,1, atomic number 1, mass number 1. So this is a normal stable hydrogen. Then H12, H13. Okay, so here protium, deuterium, tritium. Okay, so in case of a protium, you will be understanding that proton number is equal to 1. Number of electrons is equal to 1. Okay, and the number of neutron will be equal to 0. Okay, therefore the mass number is 1. 1 plus 0 is 1. Okay, proton number plus the number of neutrons gives the mass number. So what about this case? H12, here the number of protons is equal to 1. The number of electrons is equal to 1. And the number of neutrons is different. The number of neutrons here is equal to 1. Okay, there is 1 neutron and 1 proton in the case of deuterium, isotope of hydrogen. Okay, therefore the mass number is 2. 1 plus 1, 2. Now what about tritium? In case of tritium, the atomic number is 1. Therefore, number of protons is 1. Number of electrons is 1. The number of neutrons will be equal to 2 because the number of protons plus the number of neutrons will give you the mass number. Okay, that is 3. 2 plus 1, 3. Here, deuterium is H12, tritium is H13. Okay, these two lighter nuclei are combining, they are undergoing fusion, they are forming a neutron, N01, helium, Hc2, 4. Okay, so now find the atomic and mass number. So atomic number 1 plus 1, Z is equal to 2. Total atomic number, mass number 2 plus 3, 5. This is the reactant side. Next, the product side, atomic number Z is equal to 2 plus 0, 2. Mass number A is equal to 4 plus 1, 5. You can see that the atomic number and mass number are conserved. Okay, mass is released. This released mass is in the form of energy. Mass lost is in the form of energy released. Now, when 2 deuterium nuclei is taken, so 2 deuterium nuclei fuse, it forms helium, 1 neutron and 3.3 MeV of energy is produced. So, here you can see that this helium is not the stable helium atom. Stable helium atom is helium 2, 4. Okay. Now, in this case, helium 2, 3, you are able to see number of protons is equal to 2 and the number of neutrons is less than that, that is 1. Okay. It should come to a stable helium atom. So, what happens is, here we have taken 2 deuterium. Just check the atomic and mass numbers 1 plus 1, 2, 2 plus 0, 2. Okay. 2 plus 2, 4, 3 plus 1, 4. So, here you can see that the atomic numbers and mass numbers are conserved. Now, what happens to this helium is, this helium isotope then fuses with a deuterium atom. Again a deuterium atom, that is hydrogen 1, 2. And then form helium, a proton, okay, that is H11. This is a hydrogen isotope. Normal hydrogen it is. Again, energy is released, which is 18.3 MeV. Okay. So, here again you can check that 2 plus 1 atomic number is 3. 2 plus 1 atomic number is 3. Mass number 3 plus 2, 5. 4 plus 1, 5. Okay. So, what is the total energy that is released? When you are taking 3 deuterium atoms, 3 deuterium nuclei, they fuse together to form a helium atom. Okay. So, total energy will be equal to 3.3 MeV plus 18.3 MeV. That is equal to 21.6 MeV. Okay. So, in this case, you are able to see a neutron is released, then you have a proton that is released. So, here the energy released, the total energy released, a part of this energy will be the kinetic energy of the neutron and the kinetic energy of proton. Okay. This is an example to explain nuclear fusion reaction. Using deuterium atom, we are explaining this. Let us take few other examples of fusion reactions. So, first one, here we are taking 2 protons. H11 is a proton, hydrogen 11. Okay. Here we have 1 proton and 0 neutrons. 2 such protons are taken. They are combined. They are forming H12. What is H12? H12 is deuterium. Okay. During this, no neutrons is released because we don't have any neutrons here. And energy released is equal to 0.42 MeV. Comparatively, it is a small energy when you compare with this. Okay, this energy is released. Now, the second reaction, here a deuterium is taken, another deuterium is taken. Okay, so 2 deuterium atoms are taken, they are combined, then they form H13. What is H13? It is tritium. Okay, with that, another proton is released and 4 MeV of energy is also released. Just check the atomic and mass numbers. 1 plus 1, reactant side it is 2, product side 1 plus 1, 2. Okay. Mass number 2 plus 2, 4, 3 plus 1, 4. So, they are conserved. Energy released is 4 MeV. Now, the third one, here a deuterium and a tritium is taken. Okay. Deuterium plus tritium. The first reaction that we have discussed, when deuterium and tritium is taken, you will be getting a helium 2, 4. With this, a neutron is released, N01. And 17.6 MeV of energy is released. Check the atomic and mass numbers. 1 plus 1, 2. Here we have 2. Okay. This is 0. 2 plus 0, 2. Okay. 2 plus 3 is 5. 4 plus 1 is 5. So, atomic number and mass number is again conserved. So, energy released is 17.6 MeV. So, understood nuclear fusion and examples of nuclear fusion. Just In case of fission, it is splitting. In case of fusion, it is combining. Now, an important point to remember is nuclear fusion is not possible at ordinary temperature and ordinary pressure. What is the reason? So, when you consider a nuclear fusion reaction, for example, this first reaction, you are able to see that here we have H11, H11. Both of these are protons. What is the charge of a proton? Protons are positively charged. So, two positive charges, when they come close to each other, what happens? We know that like charges repulse each other and unlike charges attract each other. When two positive charges comes closer, what happens? They will experience electrostatic force of repulsion. When a positive and negative charge, that is unlike charges, comes, what happens? There is attraction. Okay, they get attracted. So here we are having two positive charges. Now these positive charges, when brought together, what happens? It will experience a repulsion. So this repulsion should be overcome. Okay, there is electrostatic force of repulsion. Only if you overcome this repulsion, they will be able to combine. If there is repulsion, we are sure that they are not going to combine. So how to overcome this repulsion? For that, we will be providing a high temperature approximately equal to 10 raised to 7 Kelvin and a high pressure. So when you provide these conditions, that is a high temperature and high pressure, the particles, due to thermal agitations, these charges, they will be acquiring a kinetic energy. Okay, this kinetic energy now helps to overcome the electrostatic force of repulsion and they will combine. So understood? This is why a nuclear fusion reaction can also be called a thermonuclear reaction. So remember, this reaction will happen only in the presence of a high temperature and high pressure. It cannot happen at ordinary temperature and pressure. You have understood what the reason is? Okay, the particles should have sufficient kinetic energy to overcome the electrostatic repulsion. We have differentiated between radioactive decay and nuclear fission. Now let us understand the distinction between nuclear fission and nuclear fusion. So first thing, to differentiate, take the definitions. Nuclear fission. In fission, when neutrons are bombarded on a heavy nucleus, it splits into two nearly equal light fragments. So here splitting of a heavy nucleus is happening. Now what about fusion? In a fusion reaction, which is happening at a very high temperature and high pressure, two light nuclei combine to form a heavy nucleus. So here it is splitting and here it is combining. Now the second point, this reaction is possible at ordinary temperature and ordinary pressure. So this was the last point that we have discussed in case of a nuclear fusion. Nuclear fusion cannot happen at ordinary temperature and ordinary pressure. The nuclear fusion reaction is possible only at a high temperature, approximately 10 raised to 7 Kelvin, and a very high pressure. Okay, now the third point, in one fission reaction, nearly 190 MeV energy is released. If you consider a fission reaction, the energy released is so much. Okay, when you consider a fusion reaction, the energy released is 24.7 MeV. Next point, fourth point, that is for the same mass, the energy released in the fission process is less than that in the fusion process. We are considering the same mass. Okay, when you take the same mass, the energy that is released in fission will be less than that in the fusion. The same point, that is for the same mass, the energy released in fusion process will be greater than that in the fission process. So got 4 points. Now the fifth point, the fissionable substance is radioactive. So what are radioactive substances we have studied? Yes, so it gives out harmful radiations and creates problems in disposal of its waste. We know the disposal of radioactive substances is very difficult. That is, it causes harm to the nature. When it is disposed in oceans or in garbages, it is not possible. Okay. Now the second is the next point, that is for a nuclear fusion reaction, the fusionable substance is not radioactive. So one is radioactive substance, fissionable substance, and fusionable substance, they are not radioactive. So it does not give out any harmful radiations and disposal of its waste is not difficult. Okay. Next point, limited amount of fissionable substances is available in nature. But when you compare it to the new fusionable substances, the fusionable substances is in abundance. Okay. Next, fission process can be controlled. We have studied, yes, controlled chain reaction. So using moderators, cadmium rod, we can control a fission reaction. So this is a use this principle in a nuclear reactor. What about a fusion reaction? It is we cannot control. Fusion reaction cannot be controlled. This is why fusion reactors could not be constructed. If it is possible to control a fusion reaction, then fusion reactors can also be constructed. Okay. Nuclear bomb. We have studied uncontrolled chain reaction. Uncontrolled chain reaction is the principle behind nuclear bomb. So nuclear bomb is based on uncontrolled fission reaction. What about hydrogen bomb? Hydrogen bomb is based on the uncontrolled fusion reaction. Okay. So we have 8 points to differentiate between nuclear fission and nuclear fusion. Let us take an example. Calculate the amount of energy released in MeV due to a loss of mass of 1 kilogram. Here we have Einstein's mass energy equivalence. E is equal to delta mc square. So mass in this case it is given 1 kilogram. Okay. C is equal to 3 into 10 raised to 8 meter per second. Now energy is equal to 1 kilogram into 3 into 10 raised to 8 whole square meter per second square. So you will be getting the energy in joules, that is 9 into 10 raised to 16 joules. Okay. Now we need the energy released in mega electron volt. So we have a relation 1 mega electron volt is equal to 1.6 into 10 raised to minus 13 joules. Okay. Then what is 1 joule? 1 joule will be equal to 1 mega electron volt divided by 1.6 into 10 raised to minus 13. Okay. So this is 1 joule. We have energy equal to 9 into 10 raised to 16 joules. So here the energy will be equal to 9 into 10 raised to 16 divided by 1.6 into 10 raised to minus 13 MeV. So when you calculate this, you will be getting 5.625 into 10 raised to 16 plus 13. Minus 13 when taken to the, here you have into 10 raised to minus 13 in the denominator. When you take it to the numerator, okay, you will be getting into 10 raised to 13. So 16 plus 13, that is equal to 5.625 into 10 raised to 29 mega electron volt. So 1 kilogram of mass. If the mass loss of mass is 1 kilogram, then the energy in MeV will be equal to 5.625 into 10 raised to 29 mega electron volt. Second example, calculate the loss in mass equivalent to the energy 1 into 10 raised to 6 kilowatt hour. So here we are given energy equal to 1 into 10 raised to 6 kilowatt hour. Einstein's mass energy relation E is equal to mc square. So here energy should be in joules, mass in kilograms and C in meter per second. Okay. Now we have to first convert this energy into the energy which is in kilowatt hour should be converted into joules. Okay. So what is the relation? 1 kilowatt hour is equal to 1000 watts into 3600 seconds, which is equal to 3.6 into 10 raised to 6 watt seconds or 3.6 into 10 raised to 6 joules. Okay. So here we have energy that is equal to 1 into 10 raised to 6. 1 into 10 raised to 6 kilowatt hour will then be equal to 1 into 10 raised to 6 into 3.6 into 10 raised to 6 joules. Okay, 1 kilowatt hour. If 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules, then 10 raised to 6 kilowatt hour will be equal to 10 raised to 6 into 3.6 into 10 raised to 6 joules. That is equal to 3.6 into 10 raised to 6 plus 6 joules or 3.6 into 10 raised to 12 joules. Okay, this is the energy that we have now. Okay. So if E is equal to mc square, we need to find m. M will be equal to E divided by c square. Here energy we got, that is 3.6 into 10 raised to 12 joules divided by, what is C? C is equal to 3 into 10 raised to 8 whole square meter per second square, which is a unit, equal to 3.6 into 10 raised to 12 divided by 3 square 9 into 10 raised to 16, that is equal to, this can be written as 36 into 10 raised to 11 divided by 9 into 10 raised to 16. 36 divided by 9 is 4 into 10 raised to 11 minus 16, that is equal to 4 into 10 raised to minus 5. What is the unit? The mass will be in kilogram. Okay. So if energy released is 1 into 10 raised to 6 kilowatt hour, the mass loss will be equal to 4 into 10 raised to minus 5 kilogram. That is in kilogram. Mass is taken in kilogram. Third example, in a nuclear fusion reaction, the loss in mass is 0.3%. How much energy is released in the fusion of 1 kilogram mass? So here we are given mass loss is equal to 0.3%. So mass loss of 1 kilogram mass will be equal to 0.3% of 1 kilogram. What is 0.3% of 1 kilogram? So if you have 0.3%, it means it is equal to 0.3 divided by 100 into 1 kilogram, or 0.3 divided by 100 kilogram is equal to 0.003 kilogram. Okay, this is a mass loss of 1 kilogram mass. Now we have to find the energy that is released. We have energy is equal to mc square equal to 0.003 into 3 into 10 raised to 8 whole square equal to 0.003 into 9 into 10 raised to 16. 9 into 3 is 27. Okay, 1, 2, 3. So we will be putting a decimal over here, into 10 raised to 16 joules, or this is equal to 2.7 into 10 raised to 14 joules. So this is the energy released. Okay, if the mass loss is 0.3%. Now let us solve an example, a question from exercise 12B, question 1. In fission of 1 uranium-235 nucleus, the loss in mass is 0.2 a.m.u. atomic mass unit. Calculate the energy released. So we have a relation, that is 1 atomic mass unit is equal to 1.66 into 10 raised to minus 27 kilogram. Okay, so we have the energy. Okay, if this is the mass lost, in the starting of the session we have explained what will be the energy in MeV. 1 a.m.u. if it is the mass that is lost, then the energy released will be equal to 931 mega electron volt. Okay, here we have 0.2 a.m.u. Then what is 0.2 a.m.u? 0.2 a.m.u will be equal to 0.2 into 931 mega electron volt. That is equal to, you will be getting 186.2 mega electron volt. So you have to remember this relation. If you don't remember this relation, first you will be having 1 a.m.u is equal to this much kilogram. With this you can find in joules, energy in joules, then the energy in MeV you can convert. So this conversion we have discussed in the starting of the session. Question 2 of exercise 12B. When 4 hydrogen nuclei combine to form a helium nucleus in the interior of some, the loss in mass is 0.0265 a.m.u. How much energy is released? So we have mass. If mass is loss is 1 a.m.u, then this is equal to energy 931 mega electron volt. Okay, here we are having 0.0265 atomic mass unit. Then this will be equal to 0.0265 into 931 mega electron volts. When you calculate this, you will be getting it to be equal to, on rounding figure you will get 24.7 mega electron volt. Okay. Again, here we are having in a.m.u. You can convert it into kilogram. Then from kilogram, how much joules it is, the energy. Then that joules can be converted into mega electron volt. Okay, this is similar to the question that we have just solved. That's all for today. In today's class, we have discussed about nuclear fission reaction, nuclear fusion reaction, distinction between radioactive decay and nuclear fission, distinctions between nuclear fission and nuclear fusion, the uses of nuclear fission and fusion. Also, we have solved questions from exercise 12B. Hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to Learnohub. Learnohub free hai, par best hai. Thank you.